In this video, we are going to draw the following parametric curve, which is given as x equals 2t squared and y equals 3t minus 2t cubed. So with this t as the parameter, and we are not going to stop there, and we are going to actually calculate the area enclosed by this parametric curve. And here the thing is, I am going to use the graphing calculator like Desmos, but only to show you the accurate version of the curve. I am not going to use the graphing calculator to sketch the curve. We are going to do that by the sheer force of the mighty calculus. So first, we must investigate the increase and decrease of the curve. So we need a derivative. Here, the derivative of the parametric curve can be obtained like this. So derivative of y with respect to x, which means the slope in the graph, can be calculated as dy over dt over dx over dt. Here, dx over dt is 4t and dy over dt is 3 minus 6t squared. And they give dy over dx 3 minus 6t squared over 4t, which will be the slope of the curve. Next, to properly sketch the curve, we also need the information about the curvature. That is, whether the curve is convex or concave. The curvature is related to the second derivative, but here do not make a mistake of writing this second derivative as d square y over dt square over d square x over dt square. This is not true. The correct expression for d square y over dx square is given like this. For simplicity, let's write dy over dx like this. Y with a dot, I'm just gonna call it y dot. Then this second derivative is simply the derivative of y dot with respect to x, which means that it is dy dot over dt over dx over dt, which simply means that differentiating dy over dx with respect to t over dx over dt. So dy over dx is given as this, so we have to use the quotient rule. The derivative of f over g is given as f prime g minus fg prime over g squared. So with that, we have 4t squared as the denominator, and at the numerator, we have f prime, the derivative of numerator, times g, the denominator, minus 3 minus 6t squared, the whole numerator, times 4, the derivative of the denominator. And dx over dt is simply 4t. So here, notice that this is 16t squared, and we can cancel out this 4 with this 16, leaving only 4 here. Therefore, we have 16t at the denominator, and in the numerator, we have minus 3 minus 6t squared. And this is the second derivative that gives the information about curvature. With these derivatives, we are now ready to investigate the curve. And in order to investigate the curve, you are going to need this increase-decrease table. But here, instead of changing x, let us actually change the parameter t here. And also let us investigate the signs of dx over dt and dy over dt as well. Next, we have dy over dx, which is the slope, so it tells us whether the curve is increasing or decreasing. And we have second derivative to investigate the curvature. With these, we are going to investigate the movement of the point x, y on the coordinate plane. Right, so first, you can notice that at t equals 0, the dx over dt becomes 0, and the sign of dx over dt is positive here and negative here, which means that if we change t values, x increases in this interval and x decreases in this interval. We can do similar for dy over dt. So from here, dy over dt is 0 at t equals minus square root of 2 over 2 or t equals square root of 2 over 2. And the sign is positive here negative here, and negative here, which means that y increases here and decreases in the interval when it is negative. And next, the slope dy over dx. From here, you can notice that this derivative is 0 here and 0 here. And what about its sign at other interval? Well, here, by investigating the sign at the numerator and denominator, which are basically these, we can find out that dy over dx is positive here, negative here, and positive here. And when t approaches 0, dy over dx diverges either to the positive infinity or negative infinity. Again, this dy over dx means slope of the graph, so it means that the curve increases here and decreases here and increases here and decreases here. And now the curvature, from here we can find out that curvature is positive here, diverges here, and negative here. It means that the curve is convex here and concave here. Right, so what is the movement of x, y? First, we can find its coordinates at some specific t values. For example, when t equals 0, the x, y is 0, 0. And from here, the coordinates are 1, square root of 2. And here, 1, minus square root of 2. So first, let's take a look at this region. Here, the negative dx over dt means that x decreases, and negative dy over dt means that y also decreases, and the curve increases, and it is convex, which means that as t increases in here, in this interval, the movement of point x, y looks like this. So x decreases, y decreases, and it is convex. And since the shape of curve is like this, it is definitely increasing from the perspective of increasing x. Then it reaches 1, minus 2. So the curve looks something like this. And then let's take a look at this interval. Here x decreases, but y increases, and the overall curve is decreasing, and it is convex. So the movement of x, y is like this. In this way, so x decreases, y increases, and the curve points this downward direction. So in this interval, x, y moves like this. Decreasing x, increasing y, curve is convex, and 0, 0 with infinite slope at the origin. Then in here, x increases, y increases, and the curve is now concave. So it moves like this and reaches 1, square root of 2. So the points move like this. And then here, x increases, y decreases, and the curve is concave, so points move like this. And we finally obtain this curve. Now here, this point is 3, 0, because from here, if we let y equals 0, then we obtain t equals 0, or t equals plus minus square root of 6 over 2, and this value gives 0, 0 here, and these values gives 3, 0, this point. Right, so we have obtained the curve, and now it's time to calculate the area. Okay, so here is our curve with specific t values are mentioned on the graph, and the area enclosed by the curve is this region. And that area is simply twice the area of this region above the x-axis, and area under a curve is simply given as integral of y with respect to x. Here the x is from 0 to 3. But here y is not given as a function of x. Actually, y is given as a function of t. And so does x. So let us change this integral into the integral with respect to t. So y is given as 3t minus 2t cubed. And from here, dx is equal to 4t dt. So we have 4t dt, and when x equals 0, t equals 0. So we have 0 here, and when x equals 3, then t equals plus minus square root of 6 over 2, and this part is where t is positive, So let's take positive values. So the upper end is square root of 6 over 2. So we have 2 integral from 0 to square root of 6 over 2, 12t squared minus 8t to the power of 4 dt. So 2 times, if we integrate, we have 4t cubed minus 8 over 5 t to the power of 5, 0, and the square root of 6 over 2. And if we calculate this, we obtained 12 square root of 6 over 5. And this is the entire area enclosed by the curve. So there you go. We have absolutely crushed this parametric curve problem without cheating with the graphing calculator. This is the sketch of the curve using Desmos Graphing Calculator. And for this moving point, I used k instead of t because t is already used to draw the parametric curve here. And you can see that from changing k value from minus square root of 6 over 2 to the square root of 6 over 2, you can see the point moves on this loop part, which we have already calculated with calculus and derivatives. So like I said, I am only using this graphing calculator to actually show you the exact shape of the curve, and I have not gained any new knowledge about the curve by Desmos. All the information we need, like increase, decrease, convex, all that stuff were purely obtained by calculus. And this is actually the general method of properly investigating the parametric curve. So I hope that the process shown in this video help you in the similar problems. And if this video was indeed useful, please hit like and subscribe to support me making more math videos. Thank you for watching, and I will see you in another video.